got ladies basketball here against Springboro. We've got boys basketball at Springboro and wrestling at home on Saturday. So if you can catch one or all of those and support the Warriors, that would be great. Have a great day.
So first of all, 7.1a, homework is not tonight's homework. Sometimes people get thrown off when I do notes in class that are different from the homework that's due. Don't let that throw you off. So in this example, seems kind of random. We're talking about the rate of potato consumption during the 1970s in Austria. Seems kind of obscure, but I'm sure the Austrian farmers find it important how many potatoes people are eating, so they know how many to grow, right? So anyway, the rate of potato consumption was given by this. C of t equals 2.2 plus 1.1 to the t power. So just for clarification, t represents the number of years since 1970, and c is the rate, and it's measured in million bushels per year. You might not know what a bushel is. A bushel is like a basket about this big. All right, so the question on A is, write a formula for the number of potatoes consumed, I guess more specifically for the bushels of potatoes consumed after 1972. So we're trying to figure out a formula for the bushels of potatoes that were consumed after 1972. Okay, so this function, it inputs time in years, and it outputs the rate in million bushels per year. So if I were to find the area on this graph, so I'm just going to make some numbers up. Let's say the rate is 5 million bushels per year. And that goes on for a time period of 3 years. So if you consume 5 million bushels per year for 3 years, then that means you're going to end up consuming 15 million bushels, right? So this diagram, this discussion is just to show you that we want to integrate the rate function to figure out how many bushels are being consumed. So our question says write a formula for the bushels that are consumed. And so that formula that we're going to write should be an integral. So we're going to integrate the rate in order to find out the number of bushels consumed. And since we want to know from 1972 to a certain year, we're going to put a 2 down here. That represents 1972. And then if we wanted to go 1972 to 1976, we would put a 6 up there, right? But we want a formula that'll output it for any year. So we're going to put an X up there. And so then our formula, I'll have P stands for the number of potatoes. The number of potatoes consumed in the year X is this. Okay, so that's not a very satisfying formula because it's got an integral in it. But this didn't say write an explicit formula. If it said write an explicit formula, then this integral symbol wouldn't be allowed in our formula. But it just said write a formula, so we can get away with having an integral in our formula. So then if the next question, if part B said, how many potatoes were consumed from 1972 to 1975, what would you do? You just put a 5 there for X, right? And then do math 9 from 2 to 5 of this formula. Okay, so that's what we're going to do for part B. How many potatoes were consumed from 1972 to 1975. So that's just P of 5. So I have to get my calculator to calculate that. So that's 10.802. What would the label be for that? It's the amount of potatoes, yes, but what are the amount of potatoes measured in? Million bushels. So good, Kasha, you're exactly right. It's the amount of potatoes, but this is measured in million bushels. So that's a lot of potatoes. It's just Austria, too. It's a pretty small country. But apparently they eat a lot of potatoes. All right. Okay, the next, we're going to shift gears and now talk about a physics concept called work. And work is the amount of effort it takes to move an object over a distance. Work is the amount of effort it takes to move an object over a distance. So if someone asked you to move an object, what would your concern be? What would your question be? So yes, both of those would be important, right? So where you're going to move it is important. In other words, more specifically, how far do you have to move it? So if someone says, I need you to move this thing a mile, that's a totally different idea than I have to move it across the room. So the distance would be important. And then Carter's exactly right. You would care how heavy it was. And even more particular than that, you would care how hard it was to move it. And heaviness would contribute to that. The surface you were moving it across would contribute to that, right? Like whether you're going uphill, whether it has wheels or not, whether you have to push it across gravel, et cetera, et cetera. Okay, so those two concepts are force, how much effort it takes, how much oomph it takes to move it, and then distance, how far you have to move it. So the two components that you would care about are force and distance. And it turns out that to calculate work, that is the force times the distance. So this is a physics formula. Work is force times distance. Okay, now the force, well, the distance, let's start with that. The distance is measured in meters if you're in the metric system. and then it's measured in feet if you're in our system. And then the force, if you're in the metric system, is measured in newtons. So Isaac Newton is the guy that had the apple fall on his head with a certain amount of force. And so he got the measurement of force named after him. How much force there is measured in newtons. So if it takes more oomph to push it, it's more newtons. Okay, now this is a bit confusing. In our system, force is measured in pounds. And that's not such a good decision because pounds is weight. But pounds is also used for force. And force is something different than weight. Force takes into account whether it has wheels or not, whether you're going uphill, et cetera, et cetera. So it's kind of unfortunate that in our system, the measurement for force and the measurement for mass are the same, as opposed to in the metric system, they use newtons for force and they use kilograms for mass. Okay, then we're taking those newtons and we're multiplying by meters. If you take newtons divided by meters, you would get newtons per meter. But if you take newtons times meters, you get what's called the Newton meter. So it's N-M. So the Newton meter is the measurement for force in the metric system. And then in our system, it's the foot-pound. And you might have noticed that that's backwards. In our system, they put the force second and the distance first. In the metric system, they put the distance second and the force first. That's just the way it is. If you say pound-foot, that's not the acceptable way to say it. It's called a foot-pound. And if you say a meter newton, that's not acceptable. It's supposed to be a newton meter. So those are the measurements for work. Okay, so now we're going to do a non-calculus example. So let's say it takes 10 Newton of force. I guess, yeah, it takes 10 newtons of force to push an object. And you are going to move it 5 meters. And then the question is, how much work will be done? It takes 10 newtons of force to push an object. You're going to move it 5 meters. And the question is how much force, sorry, not how much force, how much work will be done. Okay, so you just use the formula of work equals force times distance. So that's just 10 times 5. So you get 50. And we took newtons times meters, so we got 50 Newton meters. Okay, so that was not calculus. That was just physics. Now we're going to take this physics concept and do a calculus problem with it. So what was going on in that last problem was, no matter where you were, it took 10 newtons to move. It took a force of 10 newtons to move the thing. So if you were here, the oomph you had to use was 10 newtons. Or if you were over here, the oomph you had to use was 10 newtons. But more realistically would be that it takes different amount of forces at different points. Maybe you're going uphill some of the way, so it takes more oomph to move it. Maybe there's a gravel surface as opposed to a smooth surface. So if you're going to push it across a smooth surface, it takes less newtons than if you're going to push it across a gravel surface, et cetera, et cetera. So it's a little bit unrealistic to say that the force would be consistent, 10 newtons the whole time. So what's more realistic is that the force would change. Okay, so a machine exerts a force to pull a cart. The amount of force needed at each location is given by F of m equals m minus 3 times 400m squared. And m represents the location, aka the position, and that would be in meters. And then, of course, F is the force in newtons. So just to further solidify what's going on with this function, let's plug a 4 into this. So 4 minus 3 is 1. 4 squared is 16. And then 16 times 400 is 6,400, I think. So that means that when you're at, so here's the 0 mark. When you're at the 4 meter mark, it takes 6,400 newtons to push this thing. But then at the 5 meter mark, it's going to take a different number of newtons to push this thing. Or I guess we're pulling here. The machine's pulling this time, but still takes that much force to pull it at each of those locations. So you plug in the location, and then that outputs how many newtons it's going to take to move it at that location. Okay, so this graph here inputs the position. That's kind of strange. We usually have a function that outputs position, right? But this function inputs position in meters and outputs the force in newtons that it takes to pull this at that location. So if you do area on this graph, maybe the height is 6 newtons and the width is 2 meters. So that means you'd have a consistent force of 6 newtons for the whole 2 meters. So then you'd get 12 watts. 12 newton meters, right? When you take newtons times meters, you get 12 newton meters. And that's work, right? When you take a force times a distance, that's a work. So we should take the integral of this function in order to answer any questions about work. Okay, so yes, that's going to be the question. The question is, how much work is done in moving the cart from the 5 meter mark to the 10 meter mark? So we talked about the fact that you want to integrate this to get the amount of work. So we're going to integrate this function, m minus 3 times 400 m squared. And we're going to integrate from the 5 meter mark to the 10 meter mark. So it's possible to do this by hand, and you want to practice. You don't want to just completely stop integrating by hand. So on the homework, do some of the problems by hand, some of them not. But to save time during class, we're just going to do Math 9 for this. And it comes out to 587,500 Newton meters. So the machine is pulling the cart from the 5 meter mark to the 10 meter mark, and it's going to do that much work when doing that. So this was a calculus problem because the amount of force it takes to pull the thing is changing during the journey. Okay. So for example 4, we're going to look at a circle inside of another circle. And the radius of the inner circle is 3 centimeters. And then the thickness here, all along the outside, is half of a centimeter. And what we're going to look at is just the area of this outer strip. So how could you find the exact area of that outer strip? Take the area of the big circle minus the area of the small circle, right? So pi times 3.5 squared minus pi times 3 squared. That's if you wanted the exact area. But what we're going to actually do instead is we're going to approximate the area of the outer strip. So obviously we could find the exact area, how we talked about, but I want to look at it in kind of a strange way and approximate the area instead, because that'll help you on one of the 7.1a homework problems. Okay, so what I'm going to do is let's visualize that this was a piece of paper, and I cut out the circle, the bigger circle, and then I cut the inner circle out of it. So I've just got this ring of paper. Okay, so then what I'm going to do with that ring of paper is I'm going to cut it right here. And then I'm going to take this and fold it outwards. And so if I did that, it would kind of look like this. It's not completely physically possible to do this, but it would end up kind of looking like this. So the idea is that I cut right here, and I could curl this back around to make that, right? Okay, now this is sort of rectangular in shape. So my idea is to use the area of a rectangle to approximate the area of this strip of paper. So the area of a rectangle is base times height. And what is the height here? 0.5 centimeters, right? got area equals base times 0.5. Okay, then this from here to here is sort of this, right? And what is that length in terms of this picture? It's the circumference of the outside circle, right? This folded around, so this distance is the circumference. So if I want to find that distance, I can approximate it using 2 pi r, because that's the formula for the circumference of the circle. So 2 pi times, well, it's a little bit awkward because I have 2 different radiuses, right? The outside radius would be 3.5, the inside radius would be 3. I'll just use 3. I mean, I'm approximating. So I guess I could pick between 3 and 3.5. Maybe it would be somewhere in between 3 and 3.5. Anyway, I'm just going to go with 3. Because that's going to be easier to figure out. So then 2 times a half is 1. So the final answer is that the area is approximately 3 pi. That would be in square centimeters. Okay, so I didn't want to know the exact area, I just wanted the approximate area, because this type of area is going to help you on one of the homework problems. Okay, for part A on example 5, the question is going to be, when does the sine of 1 over x change sine on the interval 0.1, 0.2? When does sine of 1 over x change sine on this interval? So notice that this is sine SIN, which means the ratio opposite over hypotenuse. But this is sine SIGN, right? Which means what? Positive versus negative. So another way to word this question is, when does this quantity change from positive to negative, or vice versa? Okay, so to figure out when it changes from positive to negative, essentially I'm solving this equation. When is this quantity bigger than 0? AKA, when is this quantity positive? So if I want to figure out where it changes sign, I need to figure out when it's positive and when it's negative. So essentially I'm solving that inequality. Okay, so when you have an inequality, how do you solve an inequality? You figure out where it might switch from positive to negative, right? And where it might switch is when it equals 0 and also when it's undefined. So this is just going back to solving regular old inequalities. Anytime you're trying to figure out when a quantity is positive, you need to figure out when it might switch from positive to negative. And that might happen when it equals 0, and it also might happen when it's undefined. This is easier to solve, so I'm going to start with this one. This is undefined when x is 0. Because 1 divided by 0 is undefined. But we're not going to need to worry about that too much because that's not on our interval. But it's good to mention that that's an important point, solving for when it's undefined. Okay, so over here, we're trying to figure out when this quantity is equal to 0. So let's look at the unit circle. We're trying to figure out when the sine of an angle is 0. On the unit circle, the sign is the y value. So the y value is 0 at that point, 1 comma 0, and it's also 0 at that point, negative 1 comma 0. So the question is, what are these angles? Well, 0 radians, pi radians, 2 pi radians, 3 pi, 4 pi, 5 pi, et cetera, right? Or negative pi, negative 2 pi. I'm not going to write the negatives down because my interval is positive. Okay, so if this mess, if that whole mess was 0, then we'd be taking the sine of 0, right? And that would be 0. Or if that whole mess was pi, then we'd be taking the sine of pi, which is 0. So we've boiled this question down to figure out when does that mess equal 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, et cetera, et cetera, et cetera. But really, we need to solve for x, right? So now we have 1 over x. So we're going to take the reciprocal of both sides. So x equals, well, this one would be 1 over pi, right? I'm avoiding this one because I can't take 1 over 0. Well, we already knew that. We already have that here. So we've already kind of talked about that. So we have 1 over pi, 1 over 2 pi, 1 over 3 pi, 1 over 4 pi, 1 over 5 pi, et cetera, et cetera, et cetera. Okay, so I need people with calculators in the room to type these in. 1 divided by pi is easy to type in. 1 divided by 2 pi is a little bit tricky. Make sure you put parentheses. You want 1 divided by parenthesis 2 pi, right? I have something written down here, but it's hard to read, and I'm not 100% certain it's right, so that's why I'm asking you to check these numbers for me. So for 1 over pi, I got 0.318. Is that a decent number?
Yeah.
How about 1 over 2 pi? What do we got? 0.159? Huh? 1 over 3 pi? Okay. 1 over 4 pi? 0.079?
796.
So does it make sense that they keep going down? Because if you're taking 1 divided by a bigger number, you're going to get a smaller and smaller number, right? Okay, so this is out, right? It's too small. So I think these are going to be out, and these are the ones that are in. 1 over 3 pi, 1 over 2 pi, 1 over pi. Okay, so we're solving an inequality, right? Yes? Oh, yes. Sorry about that. Good. So that's out also. Good. So these are only 2 important points. Thanks, Ella. Okay. Okay, so we were solving an inequality, and those were the possible switching places, right? So then what you do is you mark those down on a number line. So 1 over 3 pi aka 0.106, is the smaller of my two important values. And 1 over 2 pi, which is 0.159. And then really I just care between 0.1 and 0.2. So that divvies up my number line into important locations. So now I need to test these intervals, right? So I'm going to pick, as a representative in there, I'm going to pick 0.103. So I'm going to take the sine of 1 divided by 0.103. And what I got is negative 0.28. So that means my quantity is negative in that interval. Now I got to try something between 0.106 and 0.159, and I use 0.14. So I'm using 0.14 as a representative of that interval to find out what's going on in that interval with my quantity. And the sine of 1 over 0.14 is 0.757 or so, which is positive. So that means that this quantity is going to be positive in that interval. And then the representative I picked there was 0.19. And that came out to about negative 0.852. Okay, so the quantity sine of 1 over x so sine of 1 over x changes sine at 1 over 3 pi and 1 over 2 pi. Okay, so solving inequalities is tough. That's all we were doing in that question so far. That wasn't calculus yet. Is everybody okay? Okay, so now I'm going to say, for part B, if f of x equaled the sine of 1 over x, what does our answer from A tell us? So if the function f of x equaled the sine of 1 over x, what did all that work do for us? Yes, and so graphically, what would that mean? It tells us where it switches. That's good. No, not the maximum and the min. Good. No, not the concavity. Good. It's something else. It tells us that it's above the x-axis. The graph of sine over 1 over x is above the x-axis from 1 over 3 pi to 1 over 2 pi, and it's below the x-axis otherwise. When the quantity is positive, that means the graph would be above the x-axis. So that still wasn't a calculus question. You guys were trying to make it into a calculus question because you assumed I would ask a calculus question too, and I kind of led you that way, right? Okay, so f of x is above the x-axis. on the interval 1 over 3 pi, comma, 1 over 2 pi. And what happens at 1 over 3 pi to the graph? It hits the x-axis, right? That's when the y value is 0. Okay, what if f prime of x equals the sine of 1 over x? What does A tell us? Yes.
That between 1 over 3 pi and 1 over 2 pi, the slope is positive.
Tells us that the slope is positive. So it tells us that f of x, if this is f prime, tells us that f of x is increasing on that interval, right? And also that there's a max at 1 over 2 pi, right? Because the slope is changing from positive to negative. But that's if this is f prime, right? If this is the first derivative. So then my final question is, what if f double prime equals the sine of 1 over x? So if f double prime equals sine of 1 over x, what does part A tell me? Yeah. Other way around, concave up. Because a positive second derivative means it's concave up. So f is concave up on the interval 1 over 3 pi, 1 over 2 pi. And there'd be inflection points at 1 over 3 pi and 1 over 2 pi, right? Okay, so that was tough because that was all of chapter 4 in 10 minutes, a summary of chapter 4 in 10 minutes. Is everybody doing okay?